Hello everyone. In the last video we came up with a solution of increasing the size of the PMOS by which we can control the rise and fall transition time. Basically we came up with a solution to match the rise and fall transition time. So what we did, we used a buffer which was slightly which was big enough than the original buffer size, but the advantage that we got was that the resistance of the PMOS and the NMOS were matched, and as a result of that we got we got a similar discharging and charging time, basically the rise time and the fall time. So we got a equal rise time and fall time. So why did we exactly got that equal rise and fall time? That is because the time required to discharge the load and the time required to charge the load, we balanced that particular time. We got an exact time for the charging and the discharging time. So that's the reason that we came up that's how we got the solution to the unequal rise and fall transition time problem. So what we'll do is, before moving forward, what actually we do is, this is what we call as clock buffers. So this kind of buffers for which the rise and fall transition time are equal, or for which the PMOS resistance and the NMOS resistance are equal, are called as a clock buffer. So that is the difference, that is the exact difference that is present between clock buffer and regular buffers. So these buffers are called as regular buffers, and this kind of buffers which has got equal rise and fall transition time, basically equal resistance for PMOS and NMOS. So that is those kind of buffers are called as clock buffers. So yeah, and in case of regular buffers, because the regular buffers are usually used in the data path and the clock buffers are usually specifically designed for a clock path, they are very custom made. They're kind of very perfectly designed to take care of this kind of scenarios. So this is a special kind of buffers that has to be used only in clock buffers, because if you kind of use this kind of buffers in the data paths also, so you will end up using a lot of this kind of buffers. So we have to be very careful that while moving into the clock path, or while implementing the clock tree synthesis, we have to make sure that the list that we provide to the clock tree synthesis step or the clock tree synthesis algorithm, it should be clock buffers. We should give the clock buffers list for the clock tree building, and this is the very obvious reasons, and this is the very important reason. There is again one more problem with this particular clock buffer, is that now since have a least resistance path over here, there's a lot of power dissipation that can happen when it goes in an off state. So we will look into all those terminologies in the later sections, but that's a disadvantage of having a clock buffer. The clock buffer consumes a lot of power. There is a lot of power dissipation that goes across the clock. It's very obvious because initially the PMOS resistance was very high, so leakage would have been very low, but in this case the resistance is low, so there will be a leak. It will be leaking whenever it is off. So, and the leakage is controlled by the resistance of the basically either the PMOS or the NMOS, but in this case the leakage will be high because you have a clock buffer which is of low resistance. So those problems are there, but it's again a manageable, this kind of problems are again a manageable problems because we don't have any solution to the high speed circuits. So we have to restrict ourselves to this solution with some penalties, basically two penalties. One is the area penalty and one is the clock power penalty. Again, the clock path is the one that consumes 75% of the chip power. So this is again a risk that we are taking. So the better way is to control the amount of clock buffers that we used in the clock path. So that is the only way, and there are other techniques also. There are power aware, there are clock gating techniques, and all those things we have slides on all those, and we'll be looking into those topics in the further videos. But let's brought this point so that we are aware that this is a good technique. No doubt this is a good technique, but there are again problems which are associated with this. So one is the area impact, which we have to live with. One is the power impact, for which we have solutions, and we'll be looking into those in the further videos. So what we'll do is now this particular complete chip, on the chip will replace all these red color buffers with clock buffers. So from a chip point of view, we won't do much changes over here. What we'll do is we'll replace all the regular buffers with a buffer and call it as C. Whenever we denote a buffer with C, it means that we are talking about clock buffers. So now we have seen all the clock buffers, all the regular buffers which was present earlier. We have swapped everything with a clock buffer. So now after swapping it with clock buffer, basically you're touching the clock tree. So once you touch the clock tree, the complete analysis needs to be done again. So complete quality check needs to be done again. So for example, we can skip the skew part, and the reason is, for example, let's say if we try to calculate the skew is for between this point and this point. The skew will be again, it will be 1 2 3 4 5 6 7 8 9 clock buffer delays, and plus some 1 2 3 4 5 6 7 8 9 10 and 10 wire delays. It will still be the same as we saw in the before, because this is just a swapping of clock buffers to regular buffers to clock buffers. So the skew will still remain the same. That's not a problem for us. The problem that we are trying to solve over here is the pulse width. So what we'll do is we'll try to look into, since now we have this particular circuit with us with clock buffers implemented, we can go ahead and check the pulse width violations. So pulse width check, sorry. So what we'll do is very similarly we'll transmit this particular waveform, the fall to rise waveform in this particular clock path, and again the rise to fall or high to low pulse from this particular clock path, and see what we get at the output. Okay, so let's start with that. So we have the skew which is met, which is almost met, and we not check it again because we have proved this thing earlier also. So we have the skew being checked. For the pulse width, we will send this particular pulse, will send this particular signal from the clock port and see what we get at the output of each clock port. So what you get at the output of each clock port is a rising waveform, a rising pulse, which is whose transition time is now, it is not much degrading compared to the one which we had at the input. And the reason is pretty simple, that the clock buffers has got they are the bigger clock buffers with the PMOS on resistance as a least one, or basically very similar to that we have for the NMOS on resistance. So now we will be seeing a waveform which is like this, whose slew is, or whose transition is matching with what we had at the input. Next we'll transmit this signal ahead, and at this point also we'll see similar kind of a similar kind of transition. Over here also we see similar kind of transition, and finally when it reaches over here, we see a very familiar transition that we had at the input. So the transition is decent enough compared to that we had in the previous one. The previous one was very bad. The slew was at something like this. In this case, the slew is 0 to the 0 to 1, or the rise transition time is better, or is much better compared to what we had before, and it is also comparable with the one that we have sent at the input. So we have a very good 0 to 1 rise transition time, which is a good news for us. Next we will be transmitting the remaining signal, which is 1 to 0 transition signal, and see what we get over here. So we check it at this point, and at this point also the transition time is well maintained. And again the reason that you see the transition time before, which was from 0 to 1 transition time, that matching with 1 to 0 transition time. The reason is again the same. The clock buffers has got their PMOS and NMOS resistances balanced. So these are basically balanced clock buffers. This kind of clock buffers are called as balanced clock buffers. So balanced clock buffers means they have balanced the resistance of the PMOS and NMOS are balanced. So that's why we call it as balanced clock buffers. So if you see the transition time over here from logic 1 to logic 0, it is still similar to what we had at the on the other side, the 0 to 1. When we finally transmit this particular thing through this complete, when you transmit this thing through complete clock buffer chain, at the output that we see is this particular waveform, which is again which is a high to low transition time. Now at the output, if you see, though the pulse width which is seen over here, this particular pulse width is very slightly bigger than that we see over here, but still it is acceptable. It is not as bad as 600 picoseconds or 700 picoseconds. It could be 520, 530 picoseconds if we actually measure. If you actually measure at this point of time, it is slightly bigger than this particular thing, but it's within the acceptable range, which is okay for us. So in this case, what we see is the pulse width is met. The pulse width check is met. Basically, the input waveform that we sent at the input, which was like 500 picoseconds, we are getting a output waveform of roughly 520, 530 picoseconds. And similarly for the other edge, also, which is a duty cycle thing. So we are getting that. So to avoid this kind of extra thing that you are seeing over here, what you can do is at the input you can send a pulse which is slightly less. For example, you can start with 490 picoseconds or 480 picoseconds of pulse. You can send the pulse something like this, so that at the output, after the complete degradation, you see a waveform which is of 500 picoseconds degradation. So that is one of the trick that you can use. Or there are other tricks. For example, you can use a clock buffer. You can use a clock buffer which is even bigger in size. So if it is even bigger in size than the previous one, which means it is even low resistance. So basically an NMOS. So basically the bottom transistor, which is NMOS, that will be of least even lesser than R. And the PMOS will be also even lesser than R. It will be matching, but you can use a clock buffer which is even bigger in size than what we saw in the previous case. So that all techniques are there, but right now what we have seen is the pulse width check is almost, we have a solution for the pulse width check, and the check is met. So we put a green tick over here. So since I'm running out of time, what we'll do is in the next video we'll start with the duty cycle, latency and clock trip power check, and see what is the amount of and see the amount for each and every one of them, and see whether those are justified or not. So let's try to look into all this in the next video. Thank you.